Welcome back to Labyrinth Academy. I'm Liyanaarachchi, your physics tutor. Before we begin today's lesson on electric motors, checkpoint questions, I strongly recommend that you should watch my previous lessons 6C1 magnetic field and 6C2 electric motor because the ideas from those lessons will help you answer today's questions. If you already watched it, perfect. Let's get started. Let's look at question 1. Describe the use of Fleming's left-hand rule. This rule helps us predict the direction of motion of force when a current carrying conductor is placed in a magnetic field. Here's how you apply it. Stretch out your left hand so the thumb, first finger and second finger are all at right angles to each other. The first finger represents the magnetic field direction from north to south. The second finger represents the current direction, which is conventional current from positive to negative. And the thumb then shows the direction of the force or movement. So in short, Fleming's left-hand rule links together field, current and force. Now let's move to question 2. We are asked to copy the diagrams and show the direction of the force on the wire in each case. In part A, we have a wire placed horizontally between the north and south pole of a magnet, perpendicular to the magnetic field. The current flows through the wire to the given direction. To work out the direction of the force, we use Fleming's left-hand rule. Point the first finger in the direction of the magnetic field from north to south. The second finger goes in the direction of the current. The thumb will then point in the direction of the force. So in this case, the force on the wire is directed downwards. That's the direction you should show with your arrow. In part B, the wire is placed vertically between the north and south pole and the current is flowing upwards. Again, apply Fleming's left-hand rule. The first finger points from north to south, showing the direction of the magnetic field. The second finger points upwards, showing the direction of the current. Now, the thumbs gives the direction of the force. In this setup, the force will be directed in the screen away from us. That's the direction of motion of the wire. In part C, the wire lies directly along the magnetic field from north to south and carries a current in the same direction. Now, if we use Fleming's left-hand rule, we notice there's no clear third direction possible because the current and the field are parallel. Mathematically, the force depends on the sign of the angle between the current and the magnetic field. Here, the angle is 0, so sine 0 equals 0. That means the force is 0. So, when the conductor is parallel to the field, it experiences no force. Many real motors use electromagnets to create the magnetic field that causes their rotator spin. Give one advantage and one disadvantage of building a motor which uses electromagnets rather than permanent magnets. Now let's look at question 3. Many real motors use electromagnets instead of permanent magnets. The main advantage is control. With an electromagnet, we can vary the current and therefore adjust the strength of the magnetic field. We can also switch the field on or off when needed. This makes the motor more flexible than if it is used permanent magnets. The disadvantage is that electromagnets require a continuous supply of current. That means the motor uses some energy just to power the field, and some of this energy is lost as heat in the coils. So, to summarize, the advantage is flexibility and control, and the disadvantage is the requirement of continuous power supply and the extra power requirements. That brings us to the end of the checkpoint questions for A2 Physics Unit 6C2 on electric motors. We have seen how Fleming's left-hand rule helps us determine the direction of force, how different orientations of current and magnetic fields affect the motion of a wire, and finally, how electromagnets compare with permanent magnets in real motors. These questions show that the motor effect is not just a classroom idea, but a working principle behind machines we use every day, from fans and washing machines to industrial motors. That's all for today's session. In the next video, we'll move on to 6C3 magnetic forces. If you found this video helpful, don't forget to like the video, subscribe the Labyrinth Academy and check out other lessons and our educational documentaries. See you next time.